In this two-part series, I will provide a breakdown of the Molotov explosion project. I'm going to show you how to make a TyFlow particle system and use the exported particles as emitters, and showcase different techniques about how to cascade liquid simulators and use the Phoenix grid texture to cascade fire and smoke, how to use the fuel burning option, and how to add voxel tuners to control the burning process. Some tips on using the volume brush mode inside the Phoenix source, how to adjust the emission curve in order to get the most detail out of your simulations, and much, much more. At this point, one would say that by the end of the video, you'll be able to create that particular effect. But this is not going to be a step-by-step tutorial. Instead, I really hope that by the end of the video, you'll have a better understanding about Phoenix and the way it works, and will be able to create not only this, but a wide range of different effects. Let's first take a quick look at the TyFlow setup. Here I have a single particle born at frame 0. I named this event parent particle. That one particle is being assigned to a simulation group 1 and export group A. There is TyIcon helper, and the particle is placed at the icon's pivot. It has a shape operator assigned to it, and the shape is set to a simple cube. At frame 20, the particle is sent to another event where it is being fired along the icon's arrow. It starts spinning in the direction it travels, and there is a gravity force applied. This makes that particle to move in an arced trajectory. The second particle that is being generated is the bottle itself. It's brought into TyFlow using a birth object operator. It is assigned to a particle group 2 and export group B and placed over the icon's pivot as well. The bottle should be connected to the parent particle and travel with it. To do that, I turned the parent particle into a phys-x shape, switched it to kinematic, and bind it to all particles that belong to simulation group 2. In this case, the single bottle shape. So in fact, the kinematic parent particle is dragging the bottle with it. The bottle particle stays in the first event until it hits the concrete column. Once it makes contact, it goes into another event where it is being fractured using a Voronoi fracture operator. The new particles have group ID 3 assigned to them so that they can detach from the parent particle. Some drag force is being applied using the slow operator, and 15% of the pieces are randomly selected and sent to yet another event and fractured once again, creating the really tiny pieces of glass. On each stage, there is a phys-x collision operator to make the pieces interact with the geometry and the floor. I made two separate export events. The first one exports all particles assigned to group A as point helpers. In this case, it is the single parent particle. I wanted to have this animated point helper so that I can have the position and orientation data that I can use later. The second export operator exports all of the bottle pieces into a TyCache sequence. In order to export TyCache, you'll need the Pro version of TyFlow. However, if you are using the free version, you can still export the pieces into individual objects or even as an Alembic file. It's not that convenient, but it will still get the job done. And one final component of that simulation is the cloth piece. I made a piece of cloth fitting through the neck of the bottle and brought it into TyFlow with a birth object operator, positioned over the same icon used for the other elements. Convert it to cloth with a cloth bind and put a collision operator. Inside the collision operator, I added a copy of the bottle that has only the outer faces. There is another copy of the bottle that also has the inside faces deleted, but this one has the top part capped. Making that capped bottle shape wasn't really necessary since a simple cube would have been enough. This only tests which cloth particles are inside of the bottle and which ones are left outside. The ones that are inside are sent to a new event. There I have them deactivated and used an object bind operator to make them travel with the bottle. The upper part, the one that is outside, is left in the first event until frame 70, then sent into another event. In frame 71, the inactive part is also sent into the same final event that now has the entire cloth active again, and there is a collision with the column and the ground being applied, as well as some gravity force. The cloth is exported as a separate Ty cache that have the Include Cloth Geometry option enabled. Again, it can be also exported as an alembic file. The reason I made the cloth simulation into a separate flow is because cloth doesn't interact with PhysX objects in general. Also, I didn't really need the precise cloth and glass pieces interaction, since it will be obscured by the explosion anyway. I just want to point out that if you want to have the cloth to be affected by the actual broken pieces, you can always use the exported Ty cache as a collider for the cloth. But since this video was not intended to be an in-depth TyFlow tutorial, let's use that setup for now and move on with setting up the Phoenix part. Before we begin, I want to draw your attention to a cool new feature that we implemented in Phoenix 5.21. This is the colorization of the modified parameters. All of the fields that changed from their default values are shown in a different color, making it easier to track your changes. What's even better is that whenever you load one of the presets available in the Phoenix toolbar, or you downloaded a scene from the examples page, it will be easier to understand which settings are modified in order to achieve a given effect. You can go into the Phoenix's preferences and change the color of the highlights. If you don't like it, or perhaps you don't need that new feature and you prefer the old look, here you can also turn it off completely and have the old look. Let's start with the first part of the liquid simulation. We have a Phoenix simulator placed where the impact occurs. This one is called PHX liquid _ cascade 01, and it will take care of the first part of the sim. The contact with the column happens in frame 71, and that's the starting frame of the simulation. The grid is set to adaptive, so it can grow as the liquid contents expand and fly outwards. The adaptivity is based on the liquid and wet map particles. These are the two particle types that can't live outside the grid, so we need to add both into the adapt by field. The expansion is limited. And the most important is the -z value. It is set to limit the expansion just before the liquid and wet map reaches the curb and the floor geometry. We don't need this simulation to interact with it. Alternatively, you can hide the floor and the curb geometry and run the simulation without it. If we don't do any of that, the liquid will splash over these objects, creating a wet map particles that will remain until the simulation's end, and this will result in a quite large and quite empty simulation grid. The simulation will be slower, and also the cache files will be substantially bigger in size since the information of those voxels, empty or not, has to be written in it, limiting the grid size in -z direction and preventing the liquid from reaching the floor and turning into wet map particles will allow it to shrink back. First, to the size of the column only, and eventually back to its original size once the wet map dries out. We still want the floor to receive some wet map particles though. These will be handled by a second simulator. This might seem like an unnecessary extra step, but in fact will help us to avoid the large empty grid. Let's focus on the settings for the first simulation for now and deal with the second cascade in a minute. In the layer that contains the sources for this first sim, we have the geometry that is used as an emitter. It is the same geometry that is used for the TyFlow simulation. There is just a retopology modifier added in order to reduce the polygon count and to create more equally sized polygons. This geometry is linked to the point helper that we exported out of TyFlow. Next, we have the Phoenix Liquid source node that has the emitter object added in it. The source uses the volume inject mode. The inject power is animated to ramp down from 200 in frame 71 down to 0 in just a few frames. Tweaking the injection power and the duration will help when shaping the liquid burst. The motion velocity is set to 1, but since we have a moving emitter, changing this to a higher or lower value might also help with directing the shape and size of the burst. And finally, we have the Ty cache fragments of the bottle. These fragments will interact with some of the fluid and might give the splash a slightly more natural look. In this case, however, having all of the fragments was actually obstructing too much of the fluid's movement, and the burst was a bit weak. So I decided to use the cull by surface area option to remove most of the smaller ones. Since this was not intended to be a close-up shot, I didn't care too much if the liquid interacts precisely with the broken glass. Removing some of the smaller pieces created holes that the liquid could escape from. In addition, getting rid of the tiny pieces made the simulation run faster. If you are using the free version of TyFlow and do not have the option to export TyCache and use the culling option, you can still export the pieces as individual objects, and you can then handpick a few of the bigger ones and hide all of the rest. There is also a turbulence force placed at the center of the impact. The location of the force helper is important in this case because it uses a spherical decay mode, and the decay begins at the helper's pivot. The size is set to 50 centimeters, so it only acts in that area. This force affects the liquid, the splash, and the mist particles. It was added there as a small tweak, meant to further break up the uniformity of the burst slightly. The simulator itself has the timescale set to 0.25. This will slow down the movement and match the speed of the TyFlow simulation. The steps per frame are set to 3. That's the number of times the grid will be calculated between frames. When there are fast-moving objects involved, increasing the calculation steps between frames will make the fluid more stable and smooth. There is a small surface tension of 0.01. This parameter is important when dealing with small-scale simulations. In this particular case, it just further smooths the surface. The droplet formation is set to 0.5. This parameter balances between the liquid forming long tendrils or breaking up into separate droplets. The size of the droplets is left to its default value of 3. The wetting option is enabled, and the consumed liquid is set to a small value of 0.05. This parameter actually affects the burst shape quite a lot. If you raise it too much, there will be less liquid particles flying outwards, since more of them will be deleted and replaced with wet map particles. Having less of the liquid will lead to fewer splashes and less mist particles. Leaving this at 0, however, will make a quite large wet spot on the surface, and you may also notice some trails left where the droplets are rolling on the concrete without being absorbed. So it is a good idea to have at least some small amount of absorption. The drying time is set to a high value of 99 seconds. It doesn't matter if it is 99 or higher. It is just a random high enough value. That's because I'll be dealing with the drying time using a particle tuner, as you'll see later. This simulator has the secondary splash and mist particles enabled. The birth threshold determines how fast the liquid should be moving in order to produce splashes. The amount of the splashes is set to 300 in the beginning and decreased to 0 at frame 100. This is because I wanted most of the particles to be generated at the beginning and less further in time. The same goes for the splash to mist parameter. This parameter controls how fast the splash particles will be transformed into mist particles. The value of 1 means that this will happen immediately. This value is animated to go down to 0 for 6 or 7 frames, meaning that no new mist particles will be generated after that. This is done because these particles will be used as a fuel source later, and I didn't really want new ones to be constantly popping out of existence. The next parameter that is animated is an interesting one. The initial velocity multiplier determines the amount of velocity that the newly generated particles inherit from their parents. Set it to a higher value and it will produce a more cloud-like shape. Lower it down and you'll get more defined trails. The trail effect was what I was aiming for, but at the same time I wanted to have the big burst in the beginning. So this one is also animated to go down from 0.8 to 0.2 in about 10 frames. There is a value that randomizes the velocity amount, but I left that at 0. The liquid-like option forces the particles to stick together and form some clumps, acting more like the liquid ones. But the goal here was to get something resembling more of a fine mist, so this is set to 0 as well. The affect liquid parameter controls the amount of the liquid that is being deleted when new splash particles are being created. I didn't want to run out of liquid and have some of it still flying until the end, but at the same time, setting it to a value higher than 0 allows the splashes to be converted back into liquid whenever they hit something. So a small value of 0.1 seemed appropriate. Let's take a quick look at the particle tuners that are affecting the simulation. These are simple expressions that are set to delete particles based on certain conditions. There is one affecting the missed particles. It'll start deleting them almost immediately when their age is between 0.05 and 0.5. The project is set to 25 frames per second, so the lower age threshold equals roughly 1 frame. The second value of 0.5 equals roughly 12 frames. The next tuner does exactly the same thing, but for the splash particles. It acts in a much smaller age range, between 0.15 and 0.18. The next one deletes wet map particles between the age of 2 and 6.5 seconds, taking care of the drying of the surface. The last one takes care of the liquid particles, but this time, instead of their age, it looks for their distance from the central column object. This one thins out the liquid if it spreads too much to the side and far away from the center. It's just a simple way to contain the splash to that area. And finally, let's take a look at the second liquid simulator. This one is linked to the first one using the Cascade simulator option. When enabled, this option will transfer particles from the first linked simulator into the second one. The liquid emitter is outside the second volume, so it is not important if it is active or not, but you can hide it just in case. You can also hide the tuners. This simulation is much simpler and doesn't need that level of control. When cascading simulators, it is important that they overlap in order for the particles to be transferred. As the first one grows, they overlap in frame 81, and that will be the starting point for the second sim. There is no point simulating before that. The timescale is set to 2.5 in order to match that of the first one. In order to generate wet map particles, the wetting option is enabled. Here I've set a small amount of liquid absorption. Consumed liquid amount is set to 0.2. The drying time is set to 6 seconds. That's just in case that you decided to hide and disable the tuner that takes care of the drying. The secondary splash and mist particles generation is enabled, so that the simulator grid will be able to adopt these particle types from the first one. Affect liquid is set to 1 so that the splashes colliding with the surfaces would be converted back to liquid. The liquid will in turn produce wet map. For more information on flip particle lifecycle, go to Chaos Phoenix documentation page, where you'll find a detailed chart and more information about each stage. You can also follow the link in the description of this video. I won't be using any of the liquid, splash, or mist particles of this second cascade in the fire simulation. They won't be rendered, and their purpose is only to create nice-looking wet spots on the floor so that it can emit fire. And as said earlier, the only reason they are generated by a second cascaded sim is to avoid a large and empty grid. With all of that done, let's now move on and take a look at the fire and smoke simulation. The fire is also split into 2 separate simulations, one for the burning cloth when the bottle is still flying towards the column, and another one starting right after the impact and simulating the fuel explosion. As before, they are called Cascade 1 and 2. Initially, I was planning to transfer the temperature values from the first simulator into the second one using a Phoenix grid texture. At some point, I scrapped that idea because I thought that this isn't really necessary, but let's take a quick detour and show you that technique. You might find it useful and use it on other setups. Here's a simple scene that has 2 fire and smoke simulators that overlap a bit. Inside the first one, there is a sphere object used as an emitter. It is added into a Phoenix source and emits temperature and smoke. The simulation grid is not adaptive, and if you simulate this, the flame is cut at the top. The second simulation uses another source that has the first simulation as emitter. The emission is set to brush mode, and the value is 100%. That means that the voxel's values will be instantly set to that value. Contrary to the injection mode, the brush mode won't create any extra pressure, and that's pretty useful in this case. By doing this, Phoenix will use the first simulator as an emitter geometry object, and it will try to determine where the surface of that object is. This is based on the mesh settings inside the rendering rollout of the first simulator. You can first check that for yourselves by going into the preview and enabling the Show Mesh option. In the rendering rollout, you can find which channel values Phoenix is using in order to create that surface. By default, it is set to smoke. You can also use any of the other channels if they are exported. You can use the temperature, the fuel, or even the speed. You can also adjust the threshold values at which the surface will be generated. However, this will only simply fill the entire object with these values. 2000 kelvins and smoke amount of 1. So there is just one final step you need to do in order to read the exact values that you need. And this is where the Phoenix grid texture comes into play. You can create two separate instances of the grid texture, both reading from the first simulator. Set the first one to read the smoke, and the second one to read the temperature. You can use those two textures as masks inside the Phoenix source. However, the source will clamp the texture between 0 and 1. The smoke channel fits perfectly in that range, but the temperature goes up to 2000 kelvins. Because of that, you need to adjust the color scale. You can always divide 1 by the highest temperature and get this really small number. But instead of doing that manually, you can hit the Rescale Grid Channel button and a dialog window will appear. Here you can set the minimum and the maximum values that you want as a result, and press the Rescale to Entire Sequence button. Phoenix will go through the entire cache sequence that you are reading through that node and will set the proper values for you. Then you can plug the grid smoke texture into the smoke mask and the grid temperature texture into the temperature mask. And that is pretty much all that you need to do. You can now start the second simulation, having essentially built a cascade system for the fire and smoke. Let's go back to our setup. The first simulation is pretty straightforward. We have the cloth piece that in my case is exported as TyCache. Since I didn't export the cloth thickness, I don't remember why. Maybe I forgot, or perhaps I wanted to have smaller TyCache files. I added a shell modifier to make the cloth thick double-sided object. Having the cloth not as a single-sided object is quite important. In order to have Phoenix properly interacting with geometry, there shouldn't be any single-sided surfaces or open edges. The cloth is added into a Phoenix source. The emission is masked with a simple black and white texture that I painted. The black part that is inside the bottle won't emit anything. The temperature mask uses the same black and white bitmap, but there is a simple animated noise multiplied on top using a standard composition node. The composited result is put through an output node, where I enabled the color map curve and lifted the black values up. Whenever you are masking a temperature with a bitmap or a procedural texture such as the noise, it is a good idea to avoid black values. Black values will emit temperature at 0 kelvins. 0 kelvins equals minus 273 degrees Celsius. It is worth mentioning that an empty Phoenix container has a default temperature of 300 kelvins, about 27 degrees Celsius. You can of course emit fluids that are colder than that, and they will start moving down instead of rising up. But we definitely don't need anything like that coming out of our burning cloth piece. The source is using a surface force emission mode, and the outgoing velocity is animated to ramp up from 0 in frame 22 to 600 in frame 24. But more importantly, going down back to 0 starting at frame 72, which is the frame right after the impact, for about 20 or so frames. At frame 90, it will stop emitting and the simulation will continue for another 30 or so frames so that all of the temperature and smoke can dissipate. This is the solution I came up with instead of the cascading simulations method that I talked about before. So the simulation starts at frame 22 and ends in frame 120. The grid is set to adaptive and the adaptivity is based on the smoke channel with a threshold of 0.05. There is also an extra margin of 2 voxels. The extra margin option expands the grid and leaves some empty space around the sim. Inside of the dynamics rollout, I have the timescale set to 0.25. This will slow down the flame and make it look as if it is in slow motion. The cooling is lowered a bit. It will take just a little bit more time for the temperature to dissipate and will make the flame taller. But the smoke dissipation is increased to 0.5 since the smoke channel is what makes the grid expand, and I didn't need the long trail of lingering smoke making a huge simulator grid. The fluidity conservation method is left at the default, direct symmetric. Since this is a fast-moving object, I increased the steps per frame to 4. Having more substeps will increase the simulation time, and at the same time, it will also smooth the velocities. But this will produce smoother flames that are not chaotic and torn apart. Inside the volumetric rendering settings, I made a custom curve and a custom gradient, but I'll talk about this a bit later. The grid will move forward, and it is important to keep the motion inertia option enabled. This option creates inertial forces in the opposite direction of the movement, making the fluid inside of a moving simulation grid to behave naturally. Having this simulation done, I can now hide it along with all the sources and other elements that were used, and in the second part of this video, we'll continue building this effect with the simulation of the main explosion.